Okay, guys, let's learn about torque. Torque is the brother of force in rigid body mechanics, and it's a very important quantity. You remember the brotherhood. I told you in linear motion we have distance, and its brother in rotational motion is angular distance, theta. Here we have velocity in linear motion and angular velocity, the brother in rotational motion. Acceleration, angular acceleration, mass, we learned in previous video, its brother is moment of inertia. And now it's the force to be connected to its brother, the torque. To learn the torque, we should start from the Newton's second law. F is equal to ma. We learned what's the brother of mass. It is moment of inertia. You remember. And on the other hand, acceleration has a brother called angular acceleration. If we multiply them, we get the torque. Torque is the brother of force. You can easily show that the SI unit of the torque is Newton meter. Don't make that mistake. Newton meter also basically is the unit of energy or work, but they are totally different quantities. Torque is a vector and has a different nature, but yeah, the unit of the torque and energy are the same. I can show you something that's an alternative formula for the torque. Here I have a mass, just a point mass at a distance r to the center, and it can go over this orbit. The force acting on that is perpendicular to the distance to the radius, and it's F, okay? Here I can write the torque acting on this mass relative to that center is I alpha, okay? And you know what the I is. For the single point mass, as we learned in previous video, I is mr square, okay? And alpha is the angular acceleration, you know. Let's break the r into rr. I can write it like that, mrr alpha, okay? And then classify them like this. This is r alpha, and I take mr here. Okay, mathematically it is still the same thing. But here we have a chance of writing r alpha as acceleration, linear acceleration. You know, linear acceleration is r times angular acceleration. So it's easily converted to mra. And then we can write it as ma times r. Mathematically, it's still the same thing, but ma, according to Newton's second law in linear motion, is force. So I can write it as force times r. Just be noted that in the fundamental and very primary model I explained, force is perpendicular to the radius. Very soon in this video, I will tell you what if the force is not perpendicular to r. So let's just check this example. It's just a very short and very important practice. Here we have a wrench, and the length of the wrench, I mean the distance from the point of the action of the force to the center of rotation is 0.3 meters, and the force acting on that perpendicular to the wrench is 120 Newton. Question is about the torque of this force. It's very easy. Just we should plug in the values. The force is 120, and the distance is given as 0.3, is also an SI unit. So I can find the torque to be 36 Newton meter. Just pay attention. Torque is actually a vector, but here in this lesson, we just continue with clockwise or anti-clockwise. Now, to find out what the direction of the torque is, you can draw a clock here, okay, with the hands, okay? Basically, this kind of force will rotate the wrench anti-clockwise. So this torque has a magnitude of 36 and direction of anti-clockwise or counterclockwise. I told you very soon I will tell you what if the force is not perpendicular to r. What should we do? Actually, this force must have an effective component. What do I mean by that? Let's establish a system of coordinate, and then let's say the force is making an angle of theta with the vertical, I mean with the radius. As you wish, of course, we can take the other one as theta. It is not that important anyway. I need this component. Actually, we started with this picture as the F is normal to the R, okay? And now I need this horizontal component that's 100% normal to R. To find it, I can just decompose the force over the horizontal axis, and this decomposition will result in F sine of theta. Why? Because in this triangle, here I have theta, and also here I must have again theta. The hypotenuse is F, and so the opposite side will be F sine of theta. Okay, so I can write the torque based on the primary introduction we had, F sine of theta times R. F sine of theta is called the effective component, or the component normal to R. We have another alternative. You can also extend the force on its line of action. This is line of action of the force, okay? And then make it like that. The distance of R, let's say the component of R to this line of action, that's perpendicular to that. So let's say this yellow dashed line is perpendicular to the line of action of the force, okay? Now we can use it as the effective component. How to find this? Let's say this is capital D. How to find it? It's very easy. You know this angle also is theta, okay? So in this triangle, here D is the opposite side of theta, and so it's hypotenuse times sine of theta again. So D is R sine of theta, okay? This is the effective distance. The component of the distance perpendicular to the line of action of the force. So I can consider that like this. I have a center like O, a distance like R sine of theta, and a force like F normal to that. Now, based on our fundamental definition, I can write it also like F times R sine of theta. So here you can opt for effective force times distance or effective distance times force. What's the meaning of effective distance? Effective distance is the distance, the component of distance that's perpendicular to the line of action. Or effective force is a component of force that's perpendicular to the distance. Okay, this is the very complete alternative for definition of the torque. So if a kind of wrench is given like this, at which the force is acting on that, making an angle of 30 degrees with the red dashed line, I mean the direction of that, or the orientation of the wrench. Here I can find the torque first by computing the component of force perpendicular to the distance. This component is that. So it's supposed to be F sine of 30 degrees, and it's 50 times sine of 30 degrees. Sine of 30, you know, is a half, so a half of 50 is 25. So basically it's a effective force of 25 perpendicular to the distance is 40 centimeter. Also it must be 0.4 in SI units, and the answer is supposed to be 10 Newton meter. It is the torque acting on this wrench. Despite of having a 50 Newton, the effective component of that, making the torque is just 25. You can also easily infer that if we have a wrench like this and the force is acting exactly to the same direction of the wrench, parallel to the wrench, the line of action is parallel to the wrench, there is no torque, you see, because the line of action is passing through the center and makes no distance. It doesn't have any perpendicular component. So in general, if I summarize that, let's say this is our wrench, and a force like F1 is acting on the wrench, and the line of action is passing through the center of rotation. It doesn't have any torque. The torque corresponding to that is 0, because there is no distance. And the best is when a force like F2 is acting on that, making an angle of 90 degrees to the distance. So here we will have the maximum torque. So the torque due to the force 2, tau 2, is supposed to be F2 times R, maximum torque. Okay, let's continue with this question. The question is very important and will have different features. Let's read it from the beginning. Two parallel forces of magnitudes F1, 3 Newton, here is 3, and F2, 4 Newton are applied to a circular disk as shown in diagram. Okay, here we have a circular disk. F1 is making an angle of 40 degrees to this radius, and F2 is perpendicular. Uh, it seems to be a couple of wheels attached to each other with different radii. Okay. Part A, calculate the magnitude of I, the net force acting on the disk. The net force. Okay, forget about the torque. This is asking just about the force. To fulfill this job, you can just consider the whole system as a point. Okay, the all forces acting on that include F1, 3, rightward, and again F2, 4, again rightward. Okay, so I just add them up. The answer is 7. It's the magnitude of the force acting on the system, net force, and also its rightward. More than that, if they ask for translational acceleration, the normal linear acceleration is supposed to be F net divided by mass. If I have the mass of the whole system, I can easily find the translational acceleration. This is, of course, indicating that the system is not in equilibrium. The reason no equilibrium is considered because it has translational acceleration. So no translational equilibrium. But let's continue for part double I of A. The net torque about the center of P of the disk. Okay, for F2, it's very easy because the torque is easily found by using F2 times the distance because it's normal to that. So it's R2. Done. But about the F1, I should make a small tweak, you know, because this is 40 degrees and F2 is not perpendicular to this radius. So I should find this component. This component is F1, let's say this is D1, okay, F1 sine of 40 degrees, and then I multiply it by D1. So it's supposed to be F1 D1 sine of 40. So I found the component of F1 perpendicular to D1. And so the answer is 0.96. The other tau 2, the torque of the second one, is very easy. Just F2 times the perpendicular distances. It has 0.2, and that's easy, 0.8. But be noted that they have opposite direction of rotation. Basically, the F1 tries to rotate the system clockwise, but F2 tries to rotate it anti-clockwise. So they partially cancel the effect of each other. Not fully cancel because this is larger. So I think the clockwise torque is larger, so it will overcome, and the total will be the total net torque acting on the system will be 0.96 minus 0.8. But however, it is clockwise because the clockwise torque is larger. Part B of the question, the moment of inertia of the disk is this. Okay, I is given because of maybe some measurements they have. Calculate the initial angular acceleration of the disk. Okay, initial angular acceleration. When they say angular acceleration, I should just remind myself the version of the Newton's second law in rotational motion. You know, basically in linear motion, I have acceleration is equal to F over mass. Now, F net, of course. Now I have alpha, the brother of F is torque net, divided by the brother of mass also is the moment of inertia. So let's use it like that. And then just plug in the values. I found the net torque in previous part, and then I is given directly in SI unit. That's all. So I will find the alpha to be 2 radian per second squared. This alpha, the angular acceleration, shows that the system is not in rotational equilibrium. So no rotational equilibrium and no translational equilibrium. The reason, net torque is not zero, so systematically this wheel will have a rotational acceleration or angular acceleration. Both forces are to the same direction, rightward, so system is acted by a rightward net force. So also it has acceleration, okay, linear acceleration. So no linear equilibrium and no rotational equilibrium. Next question. A constant force of 25 Newton is applied tangentially, you see, to the sprocket of the bicycle wheel. The sprocket is here, the center, okay? This is the cog wheel at the center. You have seen that more likely in a bicycle. The wheel accelerates from rest to an angular velocity of 40 radian per second. So from rest means that omega initial, the initial angular velocity is 0. So finally, omega final will get 40 radian per second. Okay, in time of 3 seconds. So delta t also is given. It is 3 seconds. Okay, the radius of the sprocket is given, but it's not in SI unit. It's 4 centimeter. We will convert it to 0.04 in SI. Calculate the moment of inertia of the wheel. Okay, moment of inertia is the brother of mass and is hidden in the Newton's second law. Okay, basically the total torque, the torque net, is equal to I times angular acceleration, you know. And my target is I. I'm gonna have a change in values or a checkpoint on values to get this target I. I should have I net and I should have alpha to get my goal. How to do that? It's very easy. You know that net torque is force times the radius, and it is perpendicular to that because force is tangential. So it's very easy. Net torque, torque net, is supposed to be 25 times the distance. Radius, I told you, it's not in SI unit, so it's 0.04, and that's all. Okay, the other is alpha. Alpha is supposed to be delta omega over delta t, okay? Omega final minus omega initial divided by the time. Time is also given 3 seconds, okay? So it's 40 divided by 3 because omega initial is 0. It started from rest. So we have everything. We have everything. Just we should plug in the values and find the I, our target. 0.075 kilogram meter square. As we used all quantities in SI, the answer also will be in SI units. The other question. A constant frictional torque acting on a spinning top causes its angular velocity to decrease from 150 radians per second to 80. So at the beginning, we spin this spinning top to a maximum we can, 100 omega I, initial omega 150 radians per second. Due to the friction, it will decrease and decrease to final omega of 80 radians per second. Okay, the top undergoes 300 revolutions while the angular velocity is changing. Guys, what does it mean 300 revolutions? You know, a complete revolution will imply a total angle of 2 pi, okay? So basically the total theta is for one, just one complete revolution. So the total angle of revolution when it undergoes 300 revolutions will be 300 times 2 pi. So the total theta is 2 pi times 300. The total angular distance traveled, okay? It's very important. Okay, the moment of inertia of the spinning top is this. Okay, I is given, I know that in SI unit. Calculate the magnitude of the frictional torque acting on the top. Okay, our goal is the torque, okay? We need the torque. So I should have I and I should have alpha. I know the I is given, so it's very straightforward. I just supposed to find alpha. The first thing comes to my mind is that alpha is delta omega over delta t. Okay, I know the delta omega because it's supposed to be omega final minus omega initial divided by, okay, I know final, I know initial, but what is delta t? Not given. So this way seems to be a little bit challenging because from another equation I should find delta t, and I don't want to waste my time. Okay, let's opt for another equation. Another equation would be the time independent one. You know omega final square minus omega initial square is supposed to be 2 alpha delta theta. Time independent equation. It's very similar to v final square minus v initial square in linear motion 2a delta x. You remember that? It's the same thing. Okay, so let's use it because we have everything. Final omega is 80, initial omega is given 150, and delta theta, as I told you, is 300 revolutions times 2 pi, the total angle of revolution for one single rotation. Okay, that's all. We have everything. Alpha comes negative, but we ignore it. Okay, I know that alpha is negative, but we ignore it. Basically, negative sign just indicates a decelerative motion. So this is the magnitude, the absolute value of alpha, to emphasize that we don't want to mix everything, but we know that it's negative. Okay. Anyway, I should plug in the values. Here I have the alpha, the given alpha, 5 times 10 to negative 3, and this is 4.25, the alpha we found already. Then the answer is 0.021 Newton meter. This is the total torque acting on that. This torque is a decelerative torque, and it makes the top to slow down and slow down to get 80 radians per second. Okay. Now look at this question. This is a little bit challenging. Two objects of masses 2 kilogram and 1 kilogram are attached to the ends of a weightless rod. So this rod doesn't have any moment of inertia. Supported at point P. So P will be the center of rotation, kind of pivot. As shown in the diagram, the rod is initially horizontal. Okay, the rod is initially horizontal. Guys, you know that we have a very small chance of rotational equilibrium. I mean if the total net torque acting on the system is 0, it is in rotational equilibrium. Is it? Let's check it first before I continue. Here, the weight of this, let's say G is 10, okay, is mg, and mg is 20. The other has a weight of 10, okay. This 2 kilogram will make anti-clockwise rotation, and the other a torque of clockwise. So they are fighting. Let's see if they are equal or not. The torque of this one, let's say tau 1, is 20 times the distance, 0.4, okay, in SI. The torque of the other one, tau 2, will be 10 times 0.6. Okay, the torque of this is 6, and the torque of the other seems to be 8. Oh, this is larger. So the 2 kilogram mass will have larger torque. The anti-clockwise torque is stronger. So if I leave this system from horizontal status, it starts rotating counterclockwise because the counterclockwise rotational torque is stronger. That's something you should know. If we find them equal, okay, system won't have any rotational acceleration. Determine the initial linear acceleration of each mass when the rod is released. Guys, this is linear acceleration we are looking for. Okay, let's say alpha is 10. Alpha is 10. This is just a number. We will find it, okay? This object will have an angular acceleration of alpha 10. This object also same, you know. But This 2 kilogram has a distance of 40 to the center. So linear acceleration of this is supposed to be r alpha, which is 0.4 times 10. The other will have another linear acceleration because it's in another distance to the center. Distance to the pivot is different. So this is supposed to be 0.6 times 10. Be very, very careful about that. Linear acceleration of these two objects necessarily are different, but angular acceleration same. But is it really 10? No, it is not. You remember, we had some values different. I don't think it's 10. Let's find it. Alpha is the total net torque divided by I. Okay, net torque divided by I. I found the torque. I told you this one has a torque of anticlockwise torque of 20 multiplied by 0.4, so it is 8, and the other had a clockwise torque of, as I remember, 6. Okay, so the net torque is 8 minus 6 divided by I. What the I is, guys, these are point masses. Okay, point masses. Point mass has an I like I equals mr squared. So I1 for this is supposed to be 2 kilogram times r squared, 0.4 squared. I2, the moment of inertia of the other object, will be mass times r squared, 0.6 squared. Okay, and then we add them up. So we should have m1g r1, torque of the first object, torque of the second object, y minus sign because they are against each other. One of them is clockwise, the other is anticlockwise. And these are this is the addition of the two moments of inertia. Okay, let's plug in the values. I told you upstairs is supposed to be 2, 8 minus 6, and downstairs mr squared, mr squared. So trust on my calculation, alpha is supposed to be 2.9 radian per second squared. This is alpha. Alpha is angular acceleration, but we are looking for linear acceleration. Linear acceleration of the objects are different. Linear acceleration of this one is supposed to be r alpha, 0.4 times this alpha, okay? And the other is supposed to be r 0.6 times, again 2.9. That's a different thing. Although they have the same angular acceleration, but necessarily different linear accelerations. Okay, that's the end of this question. Let's learn about the couples. What the couple is. Look at these two forces. Let's say the center of rotation is here. Center of rotation is here, okay? Two forces have line of actions passing through the center, so they don't have any rotational effect. And as they are opposite and equal, they don't have any net force. So F net acting on the system is 0, torque net acting on the system also is 0 because distance to the center of rotation for these forces is 0. Okay. Now I make them separated. When I separate them, the torque is getting larger and larger. That's very important. Okay, this is called couple. The two forces opposite and equal, but the line of the distance between the forces to the center mustn't be 0. Otherwise, they don't have any rotational effect. Okay, so when I talk about the couple, I mean we have something like a rod, wrench, whatever. And then we have two equal opposite forces like this, separated by a distance of d. Okay, both will have the same direction of rotation, same rotational effect. So if this force is making a torque of a clockwise torque, the other also is clockwise. Okay, keep in mind that the net torque is not 0. Okay, couple will have always a rotational effect, a torque, but F net is 0. It's very important. The reason, because they are opposite and equal. Okay, so the couple will not make any acceleration, linear acceleration, but they necessarily will make rotational acceleration. Okay, let's find it, what the torque could be. As I told you, let's say this is anticlockwise and this is also anticlockwise. So the total net torque making by these two forces will be force times distance d over 2 and plus, because they have the same direction of rotation, f times again d over 2. Okay, so it's very easy. This is just f times d. To find the total net torque due to a couple, we should have force, one of the forces multiplied by the separation. That's all. So, for example, let's say the wrench is like this. We have a 10 Newton of force, another 10 Newton of force, separated by a distance of 4 meters, okay? Here the torque is one of the forces, 10 times separation, 4, done. What if the forces are acting like this? They are not perpendicular to the wrench. Okay, don't bother yourself. I told you what do I mean by the distance. The distance between the forces is like this. You should extend the direction, the line of action of forces, and then this is the distance. So distance is the distance between the line of action of the forces. If they are acting like that, you will do the same thing. This is the distance. Okay? So that's very easy. So if this torque, I don't know, let's say this is 10 Newton again, this is 10 Newton, and let's say these 2 meters. So the torque due to that will be 10 times 2. This is the net torque. One of the forces times the distance. The range may be longer than 2. It may be 8 meters. It's not important for me. I just take the D. The separation between the line of action of the forces. Now the last question. Let's have a practice on the torque due to the couple. Here we have the space station. Two rocket turners, the thrusts T1 and T2, separated by distance of 80 meters. So we have two forces, 1 kilonewton, 1 kilonewton, equal and opposite, separated by 80 meters. This space station seems to be like a disk, and the diameter of the disk is 80 meters. Also the separation between the forces. The forces are parallel, and fortunately this 80 meters is exactly the separation we use for finding the torque due to the couple. Okay, are used for 30 seconds to rotate a stationary space station. Stationary, so at the beginning it has no omega. Omega initial for this space station is 0. Each of the thrusters provides a 1 kilonewton force at a right angle to the line joining the thrust. Okay, we see that. The moment of inertia of the space station about the point halfway between the thrusts is 5 times 10 to 8 kilogram meter square. Moment of inertia, so directly given. We don't want to think about any calculation, more calculation for that. Find the angular acceleration of the spaceship. Or space station. What should we do? Okay, angular acceleration is alpha. I remember acceleration was force net divided by mass. So angular acceleration is the brother of force torque net divided by mass. Divided by, I, the brother of mass. Moment of inertia. Okay, torque net is very easy because this is a couple. Just I should multiply one of the forces by the distance, the separation. Just keep in mind the force is 1 times 10 to 3 because there is a kilo. Okay, in SI it will be 1 times 10 to 3. Separation is 80. So the torque net is 1 times 10 to 3 times separation, 80. So it's 8 times 10 to 4 Newton meter. This is the total net torque. And then we have the I. So we are done. Very easy. The I is 5 times 10 to 8. So we can easily get the result. 1.6 10 to negative 4 radian per second square. Of course, it seems to be clockwise. So it's a clockwise acceleration, angular acceleration. Okay, we are done. Hope that you enjoyed the lesson and you learned a lot. Please review your notes and always be careful about maintaining your brain up to date about what you learn. You are investing on learning. See you soon and thank you for watching this video.